Okay, so we were talking about the derived functors, and if you remember that first we talked about the tore, and then we connected it to the flatness notion, and then we kind of gave a very brief introduction to Ext, and we will, of course, I'll talk about it more today. And finally, I'll come to the notion of homological dimension. So this would more or less complete our plan for the homological algebra part, which was the first part of my 12 lectures, if you have seen it carefully. So after that, we will get into regular local rings and things like that. And just a quick comment that what I had planned, but what I will not be including in this part is the notion of fiber. That I will talk about in the next lecture, because in this very homological treatment, that kind of is a bit of a mismatch. So that is pending. I'll begin with that in the next course of lectures, and then we will talk about regular rings. Okay. So quick recapitulation of the Ext modules. If you remember, I already said that this is in some sense the dual of what we did for the tore situation. So therefore, there are not much difference. If you really have understood the proofs for the tore, it is sort of very loosely speaking, it is like reversing the arrows in some sense, okay? But still, there is one small part where one has to be a little careful. I mean, there's a little difference between tore and home. That's exactly what I would like to point out, so that you are a little careful. So just to recall the definition, that you start with a projective resolution of an R module M, and then you apply this home functor, and then you know what it does. It once you have applied it, it's because of its contravariant nature. So automatically it flips the arrows, and then you have a Cochin complex, okay? And this nth homology is what is called the nth Ext functor, or the nth Ext module, okay? For this Mn. So this is how you say. So what you should remember is that when you are writing this, so one way of defining this Ext module is taking the projective resolution for the first one, okay? And then applying the home dot n. And then we will soon see that you can also do by taking an injective resolution for the second one and applying the functor home m dot. Okay, so in both the cases, you will have Cochin complexes, and then you take the nth homology, and that is what your Ext is. Okay, and once you have defined it with the help of a projective resolution, therefore it is absolutely necessary to check that it does not depend on the projective resolution you choose. And this you have already seen for tore, something similar. What you do is you just assume that there are two. You just assume that there are two such projective resolutions. One is this M star, another is M star dash, and then you can actually give a homotopy. Okay, this we had done some time back, and where we did it in terms of in a more general situation for any, we just assume that the functor has certain properties and it is additive, and we could show this, okay? And therefore here also it is applicable, and therefore because of the homotopy equivalence, you will have the maps, and that there's equality at the level of their homologies. Similarly, at the level of cohomologies. So in this case here, you have to talk about homotopy equivalence of Cochin complexes. That's the only difference. And if you remember, we did talk about it, that this was the definition. So for the chain complexes, this was the direction of the arrow of these maps H. So it was actually increasing the degree by 1. And for Cochin complexes, it is actually decreasing the degree by 1. So it is in this direction, okay? And then you have the usual requirement that if you come like this and then like this, if the addition of these two is actually the difference of F and G, okay? Where F and G are two two homomorphisms of Cochin complexes, and then you define that they are homotopic via this homotopy map H. Okay, once you have homotopy, you have equality at the level of homologies, or here homologies. So that therefore shows that the definition of X is indeed well defined, that choosing a particular projective resolution is not going to make any difference. Okay, and then comes the next one, that alternatively, we can also take an injective resolution. I already told you that for the first spot, we take a projective resolution and apply that home dot n. And for the second spot, we take an injective resolution and apply home m dot. Okay, and here again, something similar. You just show that it is independent of the injective resolution you choose. And then what is important now to show is that we have named them differently. One has been named as X, another has been named as X dash. So you have to show that they are actually isomorphic, right? So you have seen something similar, but only difference is that for Tor, both were projective resolutions, correct? So here, since you have injective resolution, but see, eventually it does not make much of a difference in the sense that you have Cochin complexes in both the cases. So you will be eventually forming a double complex, and then that proof, which we did for Tor, sort of translates with carefully reversing the arrows and modifying your argument slightly. Okay, so this is actually what you do. Yeah. So if you remember that here is going this is the projective resolution part, and then you are applying home dot n naught, then n1, then n2, and so on. And then here are the injective resolution strands, and then you are applying home m0 dot, m1 dot, and so on. Okay, then you have this full grid, and this is how you define this double complex. And this kind of situation, you have to be careful about the sign. And this is how you define the differentials, etc., etc. So the proof is essentially the same. So it is impossible to actually give the detailed proof of both. It consumes a lot of time. So I'm just saying that it follows. For these cases, if you spend a little time and try to do it on your own, and if there is still some need, we can come back to it. Okay. But now it's probably the time when we use Tor and Ext. We have already used Tor. Now we see how Ext becomes useful for us. Okay, and similar propositions that this is the one. The canonical complex homomorphisms are actually induce isomorphisms at the level of cohomologies, and therefore you have this, that whether you are taking a projective resolution and injective resolution here, then or rather. This is for the double complex, and then here individually when you are taking projective resolution and applying home, and injective resolution and applying home. So both these, they give you two different definitions of X, but you are showing that actually they are not different because both are isomorphic to this, and therefore they are isomorphic, etc., etc. Okay, and then again a similar kind of thing you did saw it for Tor, that the 0th one. So basically there we were computing kernel, here we are computing co-kernel in some sense, isn't it so? So therefore you have this, because this follows from the left exactness of the home functor. And then here that you will have, this is 0 whenever m is projective or n is injective. And this also I have just, in small letters, I have just scribbled it down, that m star given by this is a projective resolution, so a kind of trivial resolution, okay? And then similarly, you have the trivial injective resolution, and therefore, if you apply this proposition, then this follows, that you automatically have all the higher Tors, higher means on N1 onwards, they are all vanishing. I mean, sorry, higher X's, they are all vanishing because all the homologies would eventually vanish, okay? Okay, you similarly have this long exact sequence of which we call long exact Ext sequences, that if you have a short exact sequence of R modules, then you apply, so you can, obviously you understand you can have two versions. Once when you have the short exact sequence for the first place, and the other one is for short exact sequence for the second place. In both the cases, it gives rise to long exact X sequence. Okay, all kind of similar arguments. The main thing is here, because you have seen that we have had argument in general that you always have this kind of a connecting homomorphism, and this connecting homomorphism is actually the main thing in this proof, right? And because it's the kernel co-kernel map, and one uses snake lemma, etc., etc. Okay. Yeah, so now this was, this remark was something which is very, very important. I told you that this is where it is somewhat different from your Tor concept, that there are two essentially different long exact X sequences. Okay, this corresponds to the fact that X can be viewed as a contravariant functor in the first and as a covariant functor in the second variable. So I think I should kind of highlight it somehow. Okay, of the home functor. This is, you understand what is what we are trying to say. And in contrast to home, the tensor product functor is covariant in both the variables, right? And it is symmetric in the sense that when you kind of take this E tensor something or tensor something by E, they are canonically equivalent for every R module. So this is the only thing. That is why we are saying that is long exact Tor sequences are essentially the same, but for the X sequences we have. So if I take you back there, yeah. So the long exact X sequences, if you see it a little carefully, let me point out. See here when you are having this, it has flipped this, it has flipped the appearances of this M dash M and M double dash, right? See this at every spot. Okay, starts with X0, then X1, X2. So it is going as a long exact sequence in the. This is a cochain. There is no problem with that. But you see, it has flipped the order among these, the appearance of these. On the other hand, when you took this X, okay, with respect to the first one, then it hasn't really flipped the order of these N dash and N double dash. So that is exactly what is being said. So this is the thing which you have to keep in mind, which you have to be a little careful about. This problem was not there for the Tor. Okay. Okay, so more or less, yeah, just quickly, I'll tell you these two, a couple of corollaries, that if you have an R module P, then the following are equivalent, that projective, then X to N is 0 for N greater than 0 and for all R modules, and then X to 1 is 0, they are equivalent. So, so basically now this is a criteria for the projective modules involving the X. So you can see that there's a very natural connection, and what we are doing is 1 implies 2 implies 3 is fine, but 3 implies 1. So what you are supposed to prove is that you start with this short exact sequence of R modules, and then you apply the home and you want to show the exactness, and basically the vanishing of the X would definitely give you that you are having all these things 0, and therefore you will have this as a exact sequence again, and therefore P is projective. So this kind of what I was trying to tell you is that you will soon realize that there is a kind of a pattern in these proofs, and the obvious thing that you would be doing is you always apply the long exact sequence and then use the vanishing condition. Okay, this is one thing. And then when I start talking about the homological dimensions, you will see that we will use some inductive techniques, and that is also a very nice tool for proving this kind of propositions. We will come to that very soon. Okay, another piece of corollary, kind of, as I have said, that you had something involving the projective modules, and then you have something involving the injective modules. You can understand the proof is not going to be difficult. Only thing is that, let me again take you back there. So for the projective module, you had the projective condition for the one which is appearing at the first place, because if you remember, we took the projective resolution for the first place and injective resolution for the second place to define that other X. And that is therefore, you have this, this module is injective if and only if there is some vanishing of the X module happening. Okay. And a similar proof, I mean, there's hardly anything new, that you start with a short exact sequence, apply the Hom functor, and just you have to always be careful whether it is actually, you see, in the previous one, yeah, maybe I say it once again, that here this Hom functor naturally keeps this in direction intact, right? So n dash n and n double dash. On the other hand, this Hom functor actually flips the direction between m double dash m and m dash, and therefore you can see this. So that's exactly what was being said, that Ext module, this is some speciality which you don't see for the Tor, that here there's both contravariant and covariant nature for this derived functor. Okay. Okay, so this is fine. Now, gradually, I would like to go to, I stop here and then I go to the last portion of this homological algebra part, that is this homological dimensions. So let me define these carefully. And as I have said, that the proofs, if you have seen them once, understood them once, and then you would know that there is a kind of a beautiful pattern to argue, through which you argue. Okay. Okay, so let Q dot be an injective resolution of M. M is an R module. And then you say that it is of length less than or equal to n, where n is an integer, if all these all these QIs are 0 whenever I is greater than or equal to n plus 1. Okay. And you say that it is a finite injective resolution if for a large enough I, all these are 0. So that means you have a finite length, definitely. Okay. Okay, and what is the injective dimension? That is defined to be you look at all these R modules and their injective resolutions of length less than or equal to n, and then you take the infimum over that n. And now this is, you need to be a little careful that these are the sort of, these are the cases which you have to be a little careful about, that this is a non-negative integer otherwise, but you also have these two situations, plus or minus infinity. So what exactly do we mean by that? When do we say that it is plus infinity and when do we say that it is minus infinity? So look at this. We say that it is minus infinity. It's not very hard to guess. Can somebody guess and tell me when should this infimum should be minus infinity? Although it is written here, but do you really realize that this is the situation when it should be? We are saying if and only if m is 0. Kind of, can you give me some argument why we are saying this? So this infimum is minus infinity if and only if the module m is the 0 module. Why?
If m is non-zero, then it can be included inside some injective module. Mm-hmm. And so that means the infimum cannot be 0, minus infinity then.
No. Why is infimum not 0? Why are you saying it's not 0?
Maybe it is a like empty set.
Yes, yes, exactly. So, and what about this one? These are the two extreme cases which I would like to sort of bring your attention to. What about this one? We are saying that when M has no finite injective resolution, right? But this is not hard to guess, because if every injective resolution, it's never ending after finite state. You have to be a little careful when you are talking about this minus infinity, plus infinity, and 0. So what I was saying is that if M is injective, then this injective dimension is less than or equal to 0. So what you understand is when you are taking the injective resolution, so here is your module M, and then you are taking the injective modules like this. Okay, so basically your M is sort of sitting at the, if you start with this, then if you write, M and then Q0, then Q1 and so on, then this is sort of the -1th position. You can think of like this. Okay. So this is this. If you just keep that in mind, then it is not difficult to understand that when you have injectivity, then what do you mean by saying this? And when you have, but why did I write less than or equal to 0? I mean, if I have the injective dimension is less than or equal to 0, then M is injective. Can somebody tell me how to establish that fact? Because here I have said that this is a non-negative integer, right?
So either it, hello?
Yes.
Either it will be 0. In case of 0, it will be isomorphism to an injective module. And if it is less than 0, it will be -infinity. Then n will be 0.
Okay. So basically, therefore, your only three situations, you have the -infinity, you have the 0, and you have the +infinity, right? So less than or equal to 0 is also to take care of the -infinity situation, because you have the 0 module case. Please remember that, because that, you know, these kind of things keep coming back whenever you are approaching, whenever you are invoking some inductive approach and things like that. Okay. So a kind of an expected proposition that you have an integer n greater than or equal to -1. You will soon understand why am I taking greater than or equal to -1. And then M has an injective resolution of length less than or equal to n. Please remember, what is the length? This is the length. You said that the length is less than or equal to n. When the n+1th stage onwards, everything becomes 0. Okay. So this is what you should remember. And then you have this, that then the x for all these from n+1th situation, they vanish. Okay. And this is vanishing for every I and for every R module n. And then in particular for n+1, then in particular for all finitely generated modules, finitely generated R modules n, and again in particular for all cyclic R modules n. So you have seen this kind of propositions before, and once again you see it in the context of X involving the injective resolution thing. Okay. So, and again, you just sort of, these are, you know, some standard mnemonics that you are talking about whenever you are inferring something about the injective resolution thing, then that is going to come at the second spot. So, and projective resolution thing is going to come at the first spot, because X is one thing which you can use for both the purposes, right? You have already seen this. Okay. Okay. So proof is kind of expected. If I just quickly go through it, you will understand that that 1 implies 2. You start with an injective resolution of M, and you know, with the help of injective resolution of M, you can actually compute X, because all you will have to do is that you will apply the functor hom n comma dash, and then you take the homologies, and therefore it will automatically give you all these as 0 beyond n+1, because you know the length. Okay. Once you have that, then automatically you see 2, 3, 4, 5, all these things follow trivially. Now the 5 implies 1 is the one which you have to settle now. And what is the catch here? The catch here is that you only know about the cyclic R modules, and you know what the cyclic R modules and what it means, right? So here, how do you recover this situation? Now here you will see, I told you, right? This is proof by induction on M. And this inductive technique is also a kind of a very nice technique where what you do is that you kind of place your M suitably with the help of another L, okay, such that L is injective. And you know, you just show how these two injective dimensions are related, M and L. And if you show that it has dropped, expected so, right? And then automatically you infer using the inductive hypothesis, and then you finally come to the conclusion, okay, through the induction step. So this is the kind of the technique which keeps coming back for this kind of arguments. So let us still do it. But here, please remember that the important point is that you are inferring from cyclic R modules n to the general thing. Okay, so how that is important is what we should keep in mind. So n equal to -1 is the case where it begins, because we are making this conclusion for all n greater than or equal to -1. So begin with this, and then what you have is this x0, which is hom is 0. So therefore, M has the injective resolution Q dot with this Qi 0 for every I. And therefore, the length is less than or equal to -1. Okay. And then if n is 0, then if M is injective, and therefore M has an injective resolution of length less than or equal to 0. Remember, our length is length less than or equal to n. Okay. So, and here when you are inferring, here you are inferring for n plus 1, because that next stage onwards is the vanishing condition. So just keep those numbers in mind a little. Okay, I cannot show you the previous one. If I show, it becomes too small. So anyway, so now what you do is, yeah, so here comes the main technique. That what you can do is, you can actually choose an exact sequence where you have, this is injective. Okay, you can always do that, you know that, right? So once you have this L double dash, you don't worry about it. It's just some R module. And then for every cyclic R module, once you have applied this, if you take the long exact X sequence, you apply the home and then take the long exact X sequence, then you have something like this. But you know that this is 0 and therefore this is 0. Okay, because of the injectivity of L. So that was the point. So once you have that, therefore, just keep this in mind. So what you have done is, you have basically, you have taken and you have applied this. Let me just show you the specific spot. Yeah, here. Just a minute. XML and then. This should have been NL. Okay, this is not ML, this is NL. Yeah. So see, what is happening is, X, you are taking the nth stage. I did not write this, it was not important. So NL, then NL double dash, then NM, then comes again NL, NL double dash, and so on. And this, you have the 0 condition here. Okay, so you have the 0 condition here, and therefore you automatically have the, and also you have the, yeah, and also you have the 0 condition here because of the injectivity, and therefore by the induction hypothesis, L double dash has the injective resolution of length at most n minus 1. So again, let me go back just a minute. I need to show you both. Okay, so this was it, and then what you did is, you applied home n comma dot and took the long exact X sequence. Now you have the vanishing condition. Remember, you have this vanishing condition, then X10 plus 1 with NM0, where N is a cyclic R module. And you definitely say, therefore, this is the vanishing condition by 5. And you also have this, that is because of the injectivity of L. Okay, so once you have that, therefore, you are having a 0 condition with one less injective dimension. And you have the inductive hypothesis, then L double dash has an injective resolution of L, a length at most n minus 1. And then combining this resolution with the exact sequence, we get the injective resolution of length less than equal to n, because L dash appears here, right? And you have an injective module here, and therefore you have the desired length for the injective resolution. So this is exactly what I was trying to say, that putting your module at the correct place with the help of an injective module or accordingly is what you basically do for this inductive kind of argument. So let us see more such, you will understand. Now comes an immediate corollary, that we have this, the injective dimension can also be given by this soup. So you can understand that your dimension defined is through the infimum, and infimum on the length, right? And then on the length of the resolution. And then when you have the length of the resolution, then you know exactly where from the zeros start, when you have the X modules. And therefore, when you are taking this, the X modules, and if you are trying to convert that condition with the vanishing of the X modules, then basically it is the supremum for which you have the non-vanishing of the X, isn't it? Because you have already seen that whenever you have length is less than or equal to n, therefore you know that X vanishes for greater than or equal to n plus 1. So therefore this corollary indeed follows from this proposition, and instead of any R module, you can replace it by finitely generated R modules, and also you can replace it by cyclic R modules. So this is an expected one. Okay. Now, this is this one, and the one I'm going to talk about it after this. That's very, very important and very, very useful. You see what we are doing. You have a short exact sequence of R modules, and you assume that this injective dimension of this is greater than injective dimension of n. Is it necessary to assume this? Why do you think, can we not say that this, should have happened and things like that? Can somebody give me an idea? Why am I assuming this? Why do I need that the injective dimension of m double dash minus injective dimension of m is positive? Basically, we are going to prove that you have this kind of an addition formula. Injective dimension of m dash and injective dimension of m double dash, they will differ by 1. Okay. So why do you think we need this condition? This is what I'm trying to ask you. Okay, so let me again put it under. Okay, let us see. Okay. Okay. So basically you want to prove this. Okay. So what do you really want? If you look at the positions, then what you want is that if you have an injective, if you start with an injective resolution here, okay, if you have an injective resolution here for m double dash, then how you finally come to an injective resolution of m dash, okay? But here's a m sitting inside, so how you manage is the point. So let us see this. So for every R module n and for every I greater than or equal to 0, you take the long exact X sequence, okay? So you have basically applied the home n dot, okay? And then if your injective dimension is n, and injective dimension is m, so in m and m dash, if it is n and if this is m, then given conditions imply that, so now this, pay some attention to it, then given conditions imply that m is greater than or equal to 1, okay? What does that mean really?
It is not injective.
Okay, no, but now can you tell me what is the purpose behind assuming this? Not clear? Okay, good. So come here. Okay, so we are just basically considering these cases. One is if m is less than infinite, that means you have a proper injective resolution with a finite length. So you know therefore that this is 0. You know that you can give this in terms of the supremum of the non-vanishing of these X modules. So you have this, that this is non-zero for every R module n, and there exists an R module n such that this is non-zero. Oh, sorry, I wanted to write m equal to 0. I'm so sorry. Yeah, so this is the stage where it is non-zero, and from m plus 1 onwards, everything is 0 because length is at most m. And since m is greater than n by assumption, now here you are. Since m is greater than n by assumption, we have this x m. Please, I mean, like this is the problem. You have too many m dash, m and m double dash and so on. So please look at this. So you have the vanishing condition here and the non-vanishing here at the mth stage. Now you have, this is for m dash, and because of this, you have, this is also 0. Okay, obviously, because if you, is it obvious really? Can somebody tell me why this is true? Because of m greater than n?
Because injective dimension of m is m.
Correct, exactly. But is this playing any role? It is just this X sequence. Basically, you just pay attention to the X sequence. The moment you have the vanishing for this m double dash, for this M dash, I'm so sorry, for this M dash, then you automatically have for these ones. That's all. You just see where exactly this is becoming 0, because you know that for M plus, here, for M plus 1 onwards, everything will vanish, and therefore you have the correct 0 condition on all of these. Okay. So, and hence you have this isomorphism, because if you have zeros at the two ends, then the middle two are going to be isomorphic. And therefore by this exact sequence, and therefore you have the 0 condition here for all M and the non-zero condition here. And therefore the injective dimension is going to be exactly M minus 1. Just if you just sort of, you know, I mean, just keep track of it, write it at one place, write the exact X sequence and see where exactly it is becoming 0, you will be able to follow. I mean, just that here, we have to continuously change the slides. So this is the only trouble. Okay, so this was the case when M was less than infinite. And then here you have the case when M is equal to infinite. So that means what? That means for any I greater than or equal to N plus 1 whenever you have. So M is infinite means what? This is your M, please remember, okay? This is your M. So M dash is sitting here. So this is the injective dimension of M dash, okay? So that means you do not have a finite injective resolution, right? So if that is really the case, then what do you mean by, what do you mean? I mean, like, come here. So always your argument will go through this short exact sequence of X modules. Remember that. So always, I mean, this is the advantage. I mean, you don't argue through these injective resolutions. The moment you know that injective dimension is there, you always translate it in terms of the X modules, okay? And then you know that the non-vanishing condition and the soup, and therefore you know that where exactly they can be 0 and where they can be non-zero, etc. So always use this. This is the purpose behind discussing this proof. So here, once you have that, therefore you know that the two extreme terms in the exact sequence, they will be 0, okay? And therefore you have the isomorphism again here. And now if you let I be an integer greater than or equal to N plus 1, and you know this M is infinite, so there exists a module N and an integer j greater than or equal to I such that this is non-zero, because you know that it is not, you do not have any finite injective resolution. So therefore by the isomorphism mentioned above, you also have this is non-zero, and this is true for every I greater than or equal to N plus 1. Therefore you also have identity, and injective dimension of M double dash is infinite. Okay, so you see, I mean, like, only thing here is that you have to always keep track of this, these extreme cases and things like that. But your main argument is always like you transfer this to the long exact X sequence, and then you argue through the vanishing of the long exact X sequence. Okay, now this is again a very important proposition and a beautiful one. So what it says is, so if you have a non-negative integer n, and if you have this, that you have an exact sequence of R modules such that you know that the injective dimension is less than or equal to n, and you can see the length, it has gone up to qn minus 1, and then there's an n sitting out here. Qi is injective, okay, for every I, for I greater than or equal to 0 and less than or equal to n minus 1. So it is like an injective, you have the exact sequence and you have the injective module sitting here. Then, and if you know that the injective dimension is less than or equal to n, then this last one also has to be injective. Okay, so this is a very useful one. You will see, I mean, this how we can use it. So again, proof is by induction on n. Okay, so first you handle the case n equal to 0. So what does that mean? That means you have it here that your, M itself is injective in that case, right? And n is isomorphic to M. So therefore n is injective. Is this clear? Is this clear? The first one. Please look at it carefully, because that way you will be able to remember this. So n equal to 0 case is fine.
Yes, sir.
Okay, and then if you assume n is greater than or equal to 1, and if C is the co-kernel of, this is the map epsilon, and then you have this short exact sequence, okay, and this is your Q0, and this one is also exact. Is that fine with everybody? Why this is exact? So this is the co-kernel of this map epsilon. And this one, you have just put this co-kernel out here, which is in fact the kernel also, right? You have the exactness. So you have this exactness of this one. Now, if your injective dimension of M is less than or equal to 0, you know what the situations could be. One situation could be it is the 0 module, and the other situation could be what? What are the two situations? When identity, I'm sorry, always I say injective dimension, I should have written ID capital. So what is injective dimension less than or equal to 0? What are the two situations? When does it happen? The two situations are minus infinity and 0. So
it is injective or 0.
Exactly. Or you have this 0 condition. So therefore, the first equation, the first sequence splits. Here you are. Since you have injective sitting here, so this short exact will be a split exact, and C becomes injective. Is that fine? So let me put it under green. So the first sequence splits. This is basically injectivity, and C is also injective. Why is C injective? Do we know this already? Have you seen anything of this sort? That you have a split exact, you have injective here, this should be injective. Can somebody argue?
And equal to 0 case.
Yes, exactly. Okay, so therefore you have injectivity here. Now on the other hand, if injective dimension is greater than or equal to 1, then your injective dimension, you have already proved this, that how these two cases differ. So you have a short exact sequence, right? So therefore you know this formula already. So this is less than or equal to n minus 1. You're back to your inductive hypothesis. So in either case, you have the injective dimension less than or equal to n minus 1, and n is injective by the induction applied to the second sequence here. Okay. So see the, okay, so let me come to the next situation and then show you, then come back to this proposition once again. Okay, so similarly, we can define a projective dimension. So if you have a projective resolution of M, then we said that the resolution is length n. Okay, if this is 0 for all n plus 1 stage onwards, and we say that it is finite, any resolution is finite, a projective resolution, if for sufficiently large I, it is 0, every pi. And projective dimension is denoted as the infimum of these lengths, that projective resolution of length at most n, then you just collect all these n and the infimum of this. Once again, you have a non-negative integer or plus or minus infinity, and these are the three situations. That one is the minus infinity case, that is the 0. One is the less than or equal to 0 case, that is the projective, and another is the infinity case, that means it's plus infinity, means it has no finite projective resolution. So you can understand it's just a kind of a similar scenario. Okay, now here I was telling you that how the previous proposition is kind of, so you will kind of see a dual of all these things here. It's not difficult to guess, but you see how they are going to be used. Okay, so for an integer n greater than or equal to minus 1, we have a similar situation now, that M is projective resolution of length at most n, then these x modules are vanishing. Okay, so one was x of I is 0 for every I greater than or equal to n plus 1, and one is x of n plus 1 is 0. So basically, you can see what is being done. So one implies two, you know that once you know that these are all a 0, once you know that the projective resolution has length at most n, so therefore, if you take the projective resolution of M and you take the x, you know that that is one way of computing x, and then you know that it has to be 0 because all the projective modules beyond that stage have vanished. And then 2 implies 3 is obvious. And then 3 implies 1. If you have it for n plus 1, you know what to do. You basically just prove by induction on n here again. Like what you would be doing is, if n is n minus 1, then you have this situation, you know x0 is home, which implies that that is 0. So you have M is 0. So M is projective. And if you have a projective resolution of M, namely P dot, and if you know that Pi is 0, which is of length minus less than or equal to minus 1, okay, that is your M equal to 0 situation. Now, if M is projective, then M has a projective resolution of length less than or equal to minus 1. So we are just conforming with this statement, that's all. Okay, and then N equal to 0 case, that is M is projective, and therefore M has a projective resolution length less than or equal to 0. Then again, when you are going there, you just put M at the suitable spot, okay, where L is projective. So you have seen this for injective, that we put that M, L, and then L double, we wrote it, I think, L and L dash or something like that. So here again, it is just the sort of on this side. And then similar argument, please remember that whenever you do it, you kind of always come to the long exact X sequence and argue through its vanishing. That's it. Okay. You don't really play at the level of resolutions. You just apply the X, you apply the home, take the homologies, come to this long exact sequence of X, and then just see where exactly it is vanishing, and then just trace the arrows. Okay. Then you will have, see this, that you have this is 0 by the assumption, and this is 0 because L is projective. Okay. And therefore you have this is 0. So once you have this is 0, therefore this implies by the induction hypothesis that L dash has a projective resolution. So that was the purpose, that why you put like this is because you are kind of dropping the projective dimension, or in the previous one, it was dropping the injective dimension and things like that. Okay, so combining this resolution, because you have this and it has a projective resolution of length n minus 1. So that means, you know, here is the resolution. Okay, subjecting onto this, and therefore combining with this resolution, you also have a projective module sitting out here. You have a resolution with which we get of the desired length. So you can see, I told you, right? I mean, like the similarity of the arguments, the inductive techniques, using the long exact X sequence and things like that. Okay. Okay. So again, similarly, the projective dimension, you can define it using the non-vanishing of the X modules and then taking soup over these integers. And if you have an exact sequence of R modules, then you have this. And if you assume this, then you have this additive formula. And you have something similar to what we have discussed just now. So it was on this side. So here, if you have a projective resolution, not a projective resolution, but projective modules and an exact sequence formed by them. But here, when it is sitting, if you know that the projective dimension is bounded by this n, then this module has to be projective. So again, a kind of similar technique, similar proof. So all these are just parallel. So I have put them under E stroke T. Please go through them. You kind of just write it, okay, and then you will see that there is nothing new really, okay. But always, please remember that always, whenever you are using a projective resolution, that is with respect to the first spot, and therefore that home functor that you use, and the other one, when you are using injective resolution, then you use the home functor where with the first one is the fixed, and therefore you have to keep that contravariant covariant thing in mind. Okay, so be careful with that. That's it. Okay, now we are yeah. So just once more, I just want to point out that this one is rather useful, that you have bound on the projective dimension, and an exact sequence like this makes this projective. And here this was, so that's exactly what I was saying, that here you have this, that the bound on the injective dimension, and you have injective modules, you have exact sequence, then this becomes injective. Okay, so the method is by inducting on this n. Okay. Okay, so now we are see, so far we have had no assumption, some special assumption on the base ring we have been working with. And that is why every time we had to say that if it exists and things like that, okay? So we are gradually going to get a little more special. So just let me see. Oh, no, okay, okay. So first we need to talk about this corollary. Yeah, sorry, I forgot. Okay, so yeah, so now as you can see, as I've said, that probably for the first time we are assuming that R is Noetherian. Okay, and M is a finitely generated R module. Suppose the projective dimension is N, finite. Then there exists a projective resolution of M with each PI a finitely generated projective R module. So we are able to give a finite projective resolution, assuming that the projective dimension is finite. And this is under the restriction that Noetherian. You can guess why that is needed. That is actually not difficult to guess. Because what I will do is you will basically take these free modules adjecting onto M, you know it is finitely generated, and then you will keep on taking kernels and you will take free modules adjecting onto the kernel for each stage, okay? And it goes on like that, okay, such that each Fi is a finitely generated free and hence projective module. Up to this, it is fine. Now, you have come up to this stage and you know projective dimension is at most, this is N, exactly N, and that is finite. So now you are taking Pn to be the kernel of Dn minus 1. Now Pn is finitely generated. So this is where you have now used that. Is it automatic or it is happening because of something? Pn is the kernel here. So this is the Pn. Finitely generated condition on Pn.
Due to Noetherian condition.
Okay.
That submodule of a Noetherian module.
Very good. Finally, we also have projective. Why?
That's submodule.
Submodule Noetherian condition is giving finitely generated, but why projective?
Due to the last lemma.
Exactly. So there you are. Here. Okay.
The projective module.
Yes. You have the exact sequence. All the intermediate ones are projective because they were free. In our case, they are all free, and therefore you have this. So this is the need. That's exactly what I was saying. That so therefore you automatically have. So with the condition of Noetherian, you have that, and with of course with the assumption that the projective dimension is N and finite, you have this. Okay. So therefore, we have now come to some assumption on the ring, and we will be using that because otherwise, you know, I mean, if we have affine algebras in mind, or if we have local situations in mind, then we better be focused now. Okay. So yes, one more concept. This is what is called the global dimension. So global injective dimension of a ring R is you look at all the R modules and look at the injective dimensions and take the supremum. And global projective dimension is you take all the R modules, take the projective dimensions and take their supremum. Okay, so now the question is, do you have the possibility of plus infinity, etc. also? Yes, because you already have this, you know what are the possibilities for injective dimensions and projective dimensions and all. So therefore, more important than that is this fact, that both these are the same. Now, how do you prove this? Okay, so basically you want to show that this supremum and this supremum, they are the same. So this is again, I mean, something very, very interesting. So you start with a non-negative integer. Now let M be an R module such that injective dimension is greater than or equal to N. Okay. So you can guess that when you are proving two sups are the same, what exactly do you want to show, right? Okay. So then there is an R module N such that this is non-zero. Is that clear? Is that clear? How this implies this? The injective dimension is greater than or equal to N. So your X is non-zero. Why am I saying that? Because, I mean, for some R module N, of course. Otherwise, what will happen?
Because injective dimension will be less than N.
Will be from N minus 1.
Less than N.
Exactly. Will be less than. Yes. Okay. So, so therefore, you always have this projective dimension is greater than or equal to N. Why is that true? So this was injective dimension of M, and your conclusion is on the projective dimension. So that's exactly the point, that you are using this ones with respect to the first one, ones with respect to the second one. So you already know that your non-vanishing of X also gives you the projective dimension. So this is the beauty, that with the help of the first or the second, for the second one, it is the injective, and for the first one, it is the projective. So that's exactly what you have done. So on the other hand, if you assume that there is an R module n such that this is non-zero, okay, so that which implies that then you have this is greater than or equal to n. Now together, these two together, have we proved this lemma, or something more has to be done? Have we really done, or a little more is left? We are trying to prove that two soups are the same. Just remember that your injective dimension and projective dimension, they are given with the help of this non-vanishing of the X module. That you just remember. That is what is being used. Every time you use that, that's exactly the message that I'm trying to convey. Okay, so yeah. So either one of the two equal quantities, GIDR and GPDR, is what is called the global dimension, and this is GD. Basically, if you show that you do get a module for which it is greater than or equal to n, then automatically it is also greater than or equal to n. And so it is obviously reversible. Then you automatically have these two soups are matching. So how do you show that? Because you show that one soup is greater than or equal to the other soup, and conversely. Okay. Okay, so now you have this. This is what you call the global dimension. Just now we have discussed that either you do it through injective or through the projective. But this is the supremum of the projective dimensions, where M is a cyclic R module. And then that is the same as supremum of this projective dimensions, where finitely generated R module. So once again, we are back to this kind of an argument. But it's not hard to guess how this would go, because we have already proved this kind of a proposition. Yeah, some time back. Here. So we have proved this kind of a situation, that proposition, that you know that having an injective resolution of length less than or equal to n can be formulated in terms of the vanishing of this X, and even for finitely generated and cyclic modules. So therefore, you know that this is what we intend to exploit. And let me take you there. Yeah. Okay. So first situation, when you have the zero ring, then all the quantities are minus infinity. Now, when you have the non-zero ring, suppose you know that this is n. Okay. Now we only have to show that this GDR is also less than or equal to n, assuming that the supremum is this. And then we may assume that this is less than infinity. Makes sense. Okay, now for an R module n, you have this is 0 for every cyclic R module, because the projective dimension is less than or equal to n. That is what you are assuming, right? Because it is n, and that is the supremum. Okay, so therefore, you know that this is less than or equal to n. I hope this is clear to you. Fine. Because the same thing, you just use this dual nature of this X. And this being true for every R module n, we have this n is also greater than or equal to this. Okay, so basically it is nothing but using those lemma that every time. So once again, the same message, that just use this vanishing or the non-vanishing of the X accordingly, whenever you have to decide something about this global dimension, etc. But point is, why do we need this? That is the now the question. Yeah, so here we are. So I said that we have further restriction. We are taking a Noetherian local ring. If you have a finitely generated R module, then you have the following are equivalent. Now this turns out to be quite useful for our purpose. So you will see that So what are the conditions? M free, projective, flat, tori Mn is 0 for every R module n and for every I greater than or equal to 1. And that is the same as tor 1 vanishing, and not just not for every R module n, but this k is the, this R mod m. Okay, so now this is something very, very useful. Now, as I have written, I'm pretty sure that you would be convinced. Free, projective, flat, then this, okay? The tor I is 0, we all know that. Then tor 1 is 0 when you take in particular n is R mod m, the maximal ideal. And all these are obvious, or they follow from some earlier discussions. Now the only thing we need to settle is 5 implies 1. So if I have this, now here you see, here you have it for k. So you do not have it for, in general, for cyclic modules, for R mod A and all these things, right? Here you have only for R mod M. Now, how do you recover that is what is interesting. So let us prove this, okay? So what we do is, we take the minimal number of generators. M is finitely generated, don't forget. M is finitely generated. So can we not say that this minimal number of generators of M is a well-defined number and we can call it N? Can we say that? Finitely generated module over a local ring?
Yes.
So let that number be N. So then you have a free module of rank N surjecting onto M. Phi is the map, okay? And M dash is the kernel, okay? So you have this, tensorize it with the help of K as an R module, treated as an R module. Then you have this, and here you will have the tor 1. Tor 1 is 0, therefore you will have, this will be exact, right? Now, what you have is that M tensor K over R. So what is K? R mod M, right? So this is a K vector space of rank N. Is that clear to everybody? You see, this kind of argument is repeatedly used, right? So this is R mod M. So M tensor R, so basically M mod Mn, right? And then you know that since you have a minimal generator, if you take a minimal generating set here, once you go over there, then you have, this becomes linearly independent and generates. And therefore you have a vector space of rank N. So, and so is this, obviously, because you have F is free of rank N. And therefore you have this map is exactly an isomorphism. So therefore this is forced to be 0. But what is your M dash tensor K? That is M dash mod MM dash. And therefore M dash must be equal to MM dash. And then you know this is a standard Nakayama argument, okay? And therefore you have, this is 0, okay? And do you have the finitely generated condition on M dash? Is M dash finitely generated?
Yes, because it is a module of F and there are no generatings.
You have no area, so therefore. So please just be careful that you are using Nakayama, and therefore finitely generated is a requirement, okay? So therefore M is free. Okay, so you see, this is this kind of argument is essentially, so we have exploited completely that you have a Noetherian local ring, everything has been used, you have a finitely generated R module. So automatically tor 1 vanishing, tor 1 with respect to what? Or with respect to K, the residue field, R mod M. And then you get M is free. Now this is very, very useful. Okay, now I have this, that if you have M is a projective resolution of length less than or equal to N, then tor I is 0 for every R module N, and then. So basically now what we aim to do is that those assumptions which we had for finitely generated or for cyclic, question is whether with the assumption that your R is a local ring and M is a finitely generated R module, whether you can replace that N by K, that R mod M. This is the purpose behind these propositions. So basically, yes, so similar kind of argument, nothing new. So 1 implies 2, where you have the length is bounded above by N, therefore you know that all the tors will vanish if you calculate if you take a projective resolution, and if you calculate the tors, then they have to be 0. So 2 implies 3 is obvious when you take the particular case N equal to R mod M. And again, 3 implies 1. You can easily guess what it should be. That so here you have seen such an argument already. But only thing is that there your conclusion was on the freeness, but here you were just saying that since this is only for the n+1, okay? So there it was toward 1, right? So you had the freeness. Here you have the toward vanishing at the level of n+1. So it is expected that you will have a resolution of length less than or equal to n. So how you do it? Again, proof is by induction. N is equal to -1 is the first case. Then you have toward 0. Toward 0 is basically the tensor product. Tensor product is this. So if you have this with, again, Nakayama tells you that m must be 0. Okay. So therefore you have a projective resolution, etc., etc. You know what you do with the 0 module. And then now if you were, so you have basically settled this one first, n equal to -1. Then n equal to 0 case is m is projective, and therefore m has a projective resolution of length less than or equal to 0. And then you come to the n less than or equal to 1, greater than or equal to 1 situation. Now start with an exact sequence with L projective. So similar inductive argument. You have already seen this actually. So only thing is that you saw it for the X, we are doing it for the toward now. Okay. So now basically what you do is you just apply toward and then take this exact sequence. You have the vanishing condition here, and you have this is 0 because L is projective. What you have done is you have put M in a position so that there is a projective surjecting onto M. So you have the vanishing, and therefore automatically induction applies on L dash, right? And therefore you have a projective resolution of length at most n-1. And combining this, you get the projective resolution of the desired length. So this is kind of you have seen this argument before. We have seen it. We are seeing it probably for the third time, maybe. Okay. So only thing is that whether you are applying X or toward, you just keep track of the ordering. Here you don't run that risk, but for X you do because of its dual nature, right? So this is more or less how it goes. So you have now proved that your projective resolution can actually be also given. The length of the resolution can also be seen through the towed, the vanishing of the towed module. Okay, we saw that once with the non-vanishing of the X modules and things like that. And here you are seeing with respect to the vanishing of the towed module. And that too, not any towed module, but with respect to a very special one, with the assumption that you have a local ring and a finitely generated module over that. Okay, I mean, Noetherian local. Okay. And some bunch of corollaries that you can write this. The non-vanishing of the towed supremum gives you projective dimension, and the global dimension also can be written. You can understand it's with respect to R, so you can safely take it with respect to you know what global dimension is, that you just take with respect to all R modules. So in particular, you can take with respect to K. And then you can say that the projective dimension of R, global dimension of R is basically the same as the projective dimension of K as an R module. And that is then is given by this that we have seen. So only thing is that you have to settle this, that why am I saying that the global dimension of R is exactly equal to the projective dimension of R mod M as an R module. So you can, again, it's not difficult. You can see this. We have basically done similar things before, that you have the equality is given by the corollary applied to M equal to K, this one. And then the inequality holds trivially. Can somebody tell me why the global dimension of R is greater than or equal to projective dimension holds trivially? Just tell me so that I know that you are with me.
Because K
Are you saying the definition of global dimension? Yeah, it's completely broken. Somebody else? So global dimension is this, in case you have forgotten. Here it is. So, you know, this is the projective dimension. We have proved that it is the projective dimension. Basically, global dimension is, of course, I mean, like, you have first shown that global injective and global projective are the same. That is global dimension, right? So therefore, you have the supremum of projective dimensions for all R modules. So and then we prove that for R, it is in fact for the cyclic R modules or for finitely generated R modules, isn't it? So now I'm coming to a further restriction. We are saying that we will eventually just take this to be our model. That is the purpose behind doing this, right? For a local ring setup, isn't it? So is it clear now that since it is the supremum and you have for R mod m, so therefore obviously you have this inequality at least. Yeah, this inequality at least is trivially true. Now you want to show that the global dimension is less than or equal to this. Now this is interesting. See, to do so, we may assume that the this is less than infinity, makes sense. Now n, suppose this is n, and therefore you know on the vanishing of Tor, what happens, okay? And you know that with respect to both the arguments, you can flip for Tor. And therefore, for every R module m and for every I greater than or equal to n plus 1, because n is the projective dimension, therefore, by the previous corollary, you have the bound for every finitely generated R module n, and hence global dimension is less than or equal to n. Is this last part clear to all of you? Is it clear what I have said here? It's basically you are applying this, you know, this is true for all of this. So now you know, therefore, projective dimension is a supremum. So therefore this, and fine. Let me just,
yes, sir.
Okay, yeah, fine. Okay, so we are now a kind of a very useful, very, very useful corollary. So, and here we will be using something. Joydeep, are you here? Joydeep, are you here?
Yes, sir.
Okay, so I guess you have planned this. Are you going to talk about that multiplication by A for the X sequence or for the Tor, or is it one of the exercises?
It is one of the exercises. Tor I have discussed, but for X I put it
exercise. Yeah. So you have already seen this once, but X1 is the exercise. We are now going to use this here. That if you start with a non-zero divisor on M and A belonging to the maximal ideal, then once you go, you can understand that this is going to basically give you the good inductive techniques, that going modulo, taking this, going modulo this, I mean, non-zero divisor, what it does. So this, what you do is you just take this. This means the multiplication by A, okay? This is the notation. By the way, I am using Professor Balwant Singh's book for this global dimension, homological dimensions part. So I'm using his notation. So this is the multiplication by A from M to M, and you have this short exact sequence. Apply the Tor with respect to K, then you have this. And what is interesting is that these maps F and G, they are also homothesis. So homothesis means multiplication by that A, okay? But what is important here is that, see this AK, so these are by A and hence are zero because they are multiplication at the level of K, but A is in M. So therefore this is the zero map. And therefore the sequence, this is exact. And then the assertion follows from one of the previous corollaries. We have already shown that if you have this, then the projective dimension, how it gets added up. Okay, so this is the part which is very, very important here, that this map, because of A belonging to M, you have this. But can somebody tell me where exactly this non-zero divisor on M and all these have been used? Okay, think about it. Maybe I'll just put it under. Okay, so it's underlined. just to keep a mark, and we will come back that where exactly have we used it? Have we used it at all? This is the point. Okay. Yeah, so I believe, yeah, this is the one. So now you can see that let you have the last proposition I want to prove today, that if you have a non-zero divisor in R as well as a non-zero divisor on M, A belonging to M. Oops, sorry. Yeah, sorry. So you have this vanishing of the tore 1, and you have, if you have projective dimension is finite, then you have the projective dimension over this ring is also finite. So you can understand that basically going modulo is going to be used somewhere, but that will come later. Okay, so a proof is again kind of similar, that what you do is you take this, where this map is multiplication by A from R to R, and this is R mod AR, and then you have apply the tensor product, and you have this tore, and A, since A is a non-zero divisor on M, we have this is 0. Why? Why is this true? Okay, let us see the second one first. So we use the induction here on projective dimension of M. So I mean, I told you, right? I mean, like this is kind of these are the kind of typical arguments whenever you have inductive things in mind. So you have this less than or equal to 0, then M is R projective, and therefore this is also R mod AR projective. So once again, you should verify why are we saying this. Hence, this is R mod AR projective. Otherwise, your induction would not apply. Okay, so therefore you have the projective dimension less than or equal to 0. Now let us assume that this is greater than or equal to 1. This is the first one. Okay, and then here you start with an exact sequence of R modules such that P is projective. You know, you can always do this, and therefore you have this kind of a formula between the projective dimensions, and therefore you have this by induction. Okay, so now in view of 1, that is this, you have the sequence here, and that is exact, and therefore since you have the projective dimension of this one is finite, and here you have a projective module, all these things you are considering are over R mod AR, and therefore you have the projective dimension of M mod AM is also finite. Okay, so this is like kind of inductive argument. What you do is you just do it with respect to you go modulo non-zero divisor, and then you change the ring to R mod AR, and you have this kind of thing. But what was my question? So this proposition definitely is using certain things, right? So my question was, where have I used the non-zero divisor condition on M in this proof?